for Thanksgiving. Okay? One that you could do with the family around the Christmas tree. That's right. What's that? We will, yeah. If there were a pep rally today, we would already have learned the dance and we would be performing it in that pep rally today. Because typically my calculus class does a flash mob skit in the pep rallies. All calculus students it's open to them. But yeah, we did What Does the Fox Say last year. But we recruited a lot of teachers for that. It was so big you probably don't remember it. And then like 2 years ago we did Gangnam Style. And that's when a girl almost took me out at the very end. And this year, it would have been nice to have done one. If we were doing one today, y'all would have all come before school, after school. We would have learned some choreography, and we would have been dancing today. But instead, we're going to dance together in here. It's a real easy dance, okay? Well, that's what it is. It's a turkey dance. Yeah, the turkey bowl. The turkey bowl normally would be today as well. All right, example 3. The graph above is a graph of a function f of x. On the same set of axes, sketch and label a possible graph of f prime and f double prime. Okay, so this is the graph of f. Let's choose a flavor, first of all, for f prime, cherry red. Okay, so if this is f, to sketch f prime, the easiest thing is to look to see where you have horizontal tangents, if you have any, because that's going to be where your derivative is equal to what? 0. So those are x-intercepts of your function you're trying to sketch. So now maybe I'll get rid of those tangents. Now all you have to do is look to see what's happening in between there. Notice to the left of the first 0 for f prime, my function's decreasing. So my graph is going to be somewhere below, negative. And then I have an inflection value right about here, so that's going to be where it's at the highest point, somewhere right in there. And then it's going to be, well, let's see, this is where it's increasing. This is where it's 0 again. Here would be, well, let's see. -1 would be my inflection value. If we say that that's where the slopes are the steepest in the positive direction, then that's going to be the highest I go. Now, how high is that? I'm not quite sure. But then my slopes start getting smaller, right? They're still positive, but they're getting smaller, approaching 0. So it looks like that. Well, I'm going backwards, aren't I? I'm going backwards. My bad. Yeah, I'm going backwards. Let's start over. All right. Cherry red, you said? Nothing. I was thinking of a turkey dance. Horizontal tangent, x-intercept. Horizontal tangent, x-intercept. Horizontal tangent, x-intercept. Got it? Now, to the left of the first x-intercept, because our function in purple, or eggplant, is decreasing, our derivative values are going to be negative. Between -3 and 2, the graph is increasing, so our values are going to be positive. And then we're decreasing, and then it's increasing, so positive. So the shaded regions are where my derivative graph is going to live. Yeah? Okay. Now, if we want to assume that this is still going to be a vertical tangent at x equals 3, can we still assume that? Are you all okay with that? It kind of makes the problem a little more interesting. Then the slope there is going to be negative infinity. Would you agree? Because it's decreasing and it's going to negative infinity. So that's going to be a vertical asymptote on the derivative. And I know my graph is going to be going down on this side. But it's also decreasing on the other side too, right? So it's going to be negative, approaching 0. And then it's going to be increasing. Something like that. We don't know exactly what it's doing there. Now we fill in between there. At -1, that's where it's the biggest positive slope. So if I'm sketching the derivative is going to be some positive number that's a maximum. The inflection values of f become, again, remember, the local maximum and local minimums. So I can just kind of connect the dots here. If I assume that -5 is an inflection value, it's where the graph is the steepest in the negative direction. That's going to be the lowest I go, and then it's going to be something like this. And it's still decreasing, actually. It's going to be coming back up, something like that. Okay, because my slopes are like -1/2, -1, -2, and then -1/2. So something like that. Now we do have a vertical asymptote there. So that would be the graph of f prime. Now I want to sketch the graph of its derivative. So let's choose, how about beefy brown, and I'll go with a little bit thicker line quality. Green for Christmas, okay.
Thanksgiving.
All right. Sequence doesn't matter, remember? All right, so I have a 0 now. I have a 0 at -5 on my f prime graph. So I'm sketching the derivative of the red graph. So there's going to be an x-intercept. Here's an x-intercept, and that's about it, right? Now, if I'm sketching the slopes, my slopes, as I approach 3, are going to be approaching -infinity again on the left. So it should be going down again on the left. But we'll talk about what's happening on the right. Let's sketch it from left to right. My red graph is decreasing, and then it's increasing. So my slopes are going to be negative to positive. So it's going to be something like this. If this at -3 is the biggest it's going to be, because that's the inflection value, that's going to be my local max. And then it's going to come back down towards there. Now it's decreasing everywhere. I'm sorry. It's my red graph is decreasing everywhere. So this is just going to go straight down like this towards the vertical asymptote. As I come up from the other side, though, my slopes are what? Look at what happens as I come in on the other side of the vertical asymptote on f prime. My slopes are positive now, right? I'm increasing. So they're coming from a really big positive number. So that's actually going to come from up here and then pass through there. No, actually, no, I do that wrong. That's not an x-intercept. It's going to be increasing, kind of approaching, tapering off, maybe something like that. I'm not sure if it's going to approach 0. It's still increasing here, it looks like. So something like that. That would be the graph of f double prime. All right, so kind of an interesting thing, kind of looking at graphs in different ways. That's what this whole section's about. Notice again that the inflection values of f prime were the local max and mins of f double prime. All right, how about this one? If this is now the graph of f prime, now we want to sketch and label a possible graph of f. I don't think it's worth sketching f double prime, is it? Because if this is the same graph I started with up there, but now I'm calling it f prime, then if I try to sketch f double prime, it'll be exactly what I sketched up there as f prime. Yeah? What I want to do is sketch going backwards. Later on, we're going to have another name for going backwards from here. We're going to call it big F of x. But I didn't want to introduce that notation now. So let's just assume that this now is the graph of f prime, and we're going to go backwards one and sketch f. Now, we're going to be given an arbitrary starting value. In this case, f of -7 is 0. So we're going to start on the x-axis on the far left. Now we have to look at these y values in purple, or eggplant, as the slopes of the graph we're trying to sketch. What did you say? What color would you propose? Beefy brown. Okay. Okay, good. And I'm gonna go beefy, like. All right, so we're starting at -7, 0. That's not beefy enough. Let's go here. All right. From -7 to -5, I'm increasing. This is going to be a local max, right? Because it goes from positive to negative. Then I'm going to be going downhill. This is the steepest at which I go down, right there at -3. That's where my slope is the most negative. And then after that, I taper off towards a horizontal tangent line, because that's where my derivative in purple is 0. And now I'm increasing forevermore, yeah? Forevermore. But now I'm increasing at an increasing rate. up to 2. And then from 2 to 3, I'm increasing at a decreasing rate, so it's concave down. And then I'm increasing at a decreasing rate. So it's still concave down. What's happening at 3 then? That's where the slope is, well, that's okay. That the derivative of that is undefined, not the actual function. So it's still concave down. And then I horizontal out right there. And then it's increasing concave up. So then it turns like that. So that's where we get the horizontal tangent, but it looks like x cubed. It's not actually turning around. Okay, it's approaching like it's going to. I'll kind of trace through with orange. Oops. It's approaching like it's going to turn around, but then it makes like a good football move and then jukes and goes up. So now it's really looking like Thanksgiving, right? Mm-hmm. I don't either. I thought it was an answer. There you go. Those are that. The turkey looks like it has a leaf on its breast. That's a snake going to a Thanksgiving costume party. He's going as a turkey. The snake is going as a turkey. Yeah. Oh, okay. Let's do example 4, and we'll call it a day, and then we'll look at something else. Okay, we'll call it a week actually. For each of the following graphs of f prime, sketch a possible graph of both f and let's call. Oh boy, yeah. We fix it as we go. Remember, this is the first year I'm using these. I redid this in the summer, so we'll do f double prime. That's what I meant. I don't want you just to trace over the graph that's there. All right, that would be like a pre-AP type problem, not an AP. So we're gonna sketch one going forward and one going backwards. Okay, that's essentially what we're doing. One going forward and one going backwards. So this one here, if that's f prime, what would you rather do first? You want to graph its derivative or graph its what will become known as the antiderivative? The antiderivative? Okay. So I'll use green for that. So these values now represent the slopes. So I have a slope of 0 at 5. That's good. And it's increasing the whole time. So I need some place to start, and it's arbitrary. Because my slopes then are going to be positive from 1 to 5, I'm going to going uphill the whole time. I'm going to start arbitrarily low, just right here. Are you okay with that? Okay, thanks. Were you really going to take our blessing? Huh? Were you actually going to take our blessing? No. So from what becomes from 1 to 2, since the slopes are negative, f double prime is negative, and the graph is concave down. And then the slopes are positive from 3 to 4, so it's concave up like a cup. Now the slope is defined right there at 3, okay? Because the function value there is 3. To the right of there, though, it's what? Still increasing, but the slopes are negative, so it's concave down forevermore. So I'm not sure what that looks like there. Maybe something like that. So that's an arbitrary graph of f. And of course, depending on the y value where you start, it could slide up and down and be anywhere there. The thing is that these only differ by a vertical shift, right? So this could be like f of x plus some constant. This could be f of x plus another constant. This could be f of x minus a number. When you take the derivative, what happens with that constant? It goes to 0. So when we start going backwards, when we start finding antiderivatives, you're going to see that we need to make the allowance for some vertical shift, for some plus a constant that could have been there beforehand that we lost information about when we took its derivative. Okay, so now to take the derivative, we'll use red for Thanksgiving. And now I have a horizontal tangent line at 2, so that's going to be an x-intercept. My function is decreasing, so it's going to be negative. It's positive from 2 to 3, so it's going to be it's increasing, so it's positive. Now, here's where it gets interesting. I'm sketching the slope of f prime. What do we know about the value of the slope at 3 on the f prime graph? It's undefined, right? It's undefined. So I would have an open circle there. That little piece kind of looks like a parabola, which can help you sketch the derivative. It kind of looks like a line when you take the derivative using the power rule. And then everywhere to the right, the slope appears to be down down 3 over 2, so negative 3 halves. Negative 3 halves then is going to look something like this, just a horizontal line. And what would the value of derivative at the endpoints technically be? Undefined as well, so you could even fancy it by putting open circles at the end. That would be the graph of f double prime. Then you can come in here and make a tree. Yep, a Thanksgiving tree. Right. All right, we're done for the week. I don't see any sense in going on. We'll pick up with example 5 and 6 on the Monday we get back, and that's it. Then we'll test on, oh, yeah, I don't want to do that one. Let's do it. Gosh, dang it. I'm sorry. I'll do it real quickly for you. How about that? You just pay attention. Okay, see. Let's do the derivative real quickly in blue. If we're analyzing the slopes, notice to the left of 0, my function is monotonic decreasing. So my slopes are going to be negative as well. My y values on my slopes are going to be negative. And my slopes are what? Increasing or decreasing? The slopes are going from like negative 1/2 to negative 1 to negative 2 to negative 5 to negative 1,000,000. They're actually decreasing, right, because they're becoming more negative. They're getting steeper, but they're getting more negative. So the derivative of f prime is going to look something like that. It's almost going to be like the exponential piece. It'll look very similar to that. On the right-hand side, though, that graph is increasing or decreasing. It's decreasing. And so they're coming from like negative infinity to negative 10 to negative 5 to negative 1 to negative 1/2, approaching 0. So they're coming from negative infinity approaching 0. So it's going to look like that. So the piece on the left stays the same. The piece on the right jumps down. And that would be f double prime, yeah. And now we'll use purple nurple for the antiderivative. All right, so if we're going backwards, again, we need an arbitrary place to start. If I then say that the y values are the slopes that I'm looking at, since my slopes are negative and small, my y values are going to be negative. My function is going to be decreasing, at a small rate, and then decreasing at an increasing rate. So it'll actually look very similar, but you could draw it there, or you could draw it where? Up there, or there, or there. It could be anywhere. It could be anywhere you want. But just for the same reason that the derivative of what we just drew looks the same, the antiderivative will look the same. The only difference is we don't know where the y value is. So I'm going to close my eyes and slide my finger up and down, and y'all going to tell me when to stop. No one tell them to stop. Okay, nice. Good. Okay, so this would be the graph of the antiderivative. Now on the other side, I'm looking at the red graph, right? That's my original graph. These are the y values that represent my slopes. So notice because these red values are positive, my function is increasing. And as I go from right to left, it goes from a big positive number, so it's going to be a very steep positive slope. As I go to the right, my y values are decreasing, approaching 0. So my slopes are still positive but approaching 0. So it's going to look something like this. And of course, that piece could also be where? Anywhere, as long as it coincides with the x. So how about right? How about right there? And there would still be a vertical asymptote there. All right? So sketching graphs of derivatives And sketching graphs of what becomes known as antiderivatives, kind of an important skill. You're looking at the same graph in two different ways, and it's a great mental activity. All right, we'll finish the notes on Monday, and y'all's test, remember, is Tuesday. So we should be able to finish the notes and then discuss what would be on the test. Yeah, I get to make the test over the 1 week Thanksgiving break.